Hello everyone, I'm Kyle. Work at Cloudflare. I'm a systems engineer, and one of the things I work on a lot is the crypto side of things for our security stuff. So truth be told, the past month I've been in C doing TPM stuff, but we just released a package called CFSSL, which has a lot of SSL toolkit stuff that we built to be less of a pain than the OpenSSL tools. So tonight, I just want to give you guys kind of a brief introduction to the different packages for cryptography and Go. Kind of let you guys know what's available. I'm going to talk a little bit, give kind of a brief background about crypto, just for people who may not really know much about it, and then we'll just kind of look at some packages and some examples. And then I think I'll post the slides to the meetup page tonight. You guys can look at it afterwards too. And this time I kind of gave this talk at the last Go session, and now I have notes based on how that went. So what are we trying to do, first of all, like with crypto, right? We have three goals. You want confidentiality. You don't want people to be able to eavesdrop on your messages. You want people to be able to read them. You want integrity, to make sure that nobody has tampered with it or messed with it. And you want authenticity, to make sure you're talking to who you think you're talking to. And you need all three to have a secure system. If you have integrity and not authenticity, I can read what you're saying. If you have confidentiality and authenticity but not integrity, cool. Let's see. Does this work? I don't want it to just suddenly boom, so. All right. So if you have a system with confidentiality and authenticity, but no integrity, it means I can change messages en route. And I don't necessarily have to know what they are to still have an effect on them. And if I have confidentiality and integrity, that's great. The message is secret. I can't change it, but I could forge something or pretend to be who you think you're talking to, but it's actually me. So there's actually a couple different kinds of crypto, right? We have symmetric, which is what you guys may think of when you think of cryptography. It's like AES and HMAC and stuff like that, and they're very fast building blocks, but it's really hard to share keys with them. Sharing keys like this with symmetric cryptography is like sharing a password. Then we also have public key cryptography, like RSA or elliptic curves. And this is a lot easier. I have a secret that I keep and don't give to anybody, and then I give everybody a public part of my secret. So then everybody can use the public part to send messages to me, and we can build secure systems that way too. And really, we want to mix the two together. We want to use public key cryptography, which is slow but really nice to change or exchange keys. We want to use that to exchange symmetric keys. Then once we've exchanged those symmetric keys, often called a shared key, we can then move to a lot faster crypto. So one of the things that's really nice is I came from a background in C, and I'm used to using libgcrypt or OpenSSL, and it's a mess. So Go has some really nice crypto packages. They're very clean. They're very easy to use. So here's a couple of them right here. I guess we have different tools for all this stuff. Things that were a lot more difficult to do in C or in Python maybe. I don't know if you guys have Python ever messed with PyCrypto. It can be kind of a pain to get started with. Go is actually a lot easier than that. So for random data, right, that's the basis of all crypto stuff. If you want to get random data, do not use math rand. It's not meant for cryptographically secure stuff. There is, however, CryptoRand, which uses your operating system's random number generator facilities to do things securely, and that's what you should use. Rand.reader is an IO reader. We all love IO readers, right? They're awesome. So you can use it just like you would any other file or reader at all. And so it's actually pretty simple. Just like you would read stuff from a file, you would read it from that IO reader. Let's see, we can actually could run it once. Okay, so we got some cool numbers there. They're random, I promise. And we'll see again. We get different numbers, I hope, or maybe not. So this is running on App Engine, and I'm guessing the sandbox is kind of like, yeah, here's a random number generator. It's real random. So the fun part is we'll all get the same RSA keys when we run the key generation. Use that for secrets. Hashing stuff, right? The SHA hashing functions, there's stuff for that, and they're really easy to use. There is an MD5 package. Please don't use it for crypto stuff. Unless you're implementing a specification and it says use this, don't use it. And try to avoid SHA-1. There's no official weaknesses in it yet, but it's starting to show its age, and we have much better options for that. And we use hashing for building blocks in a lot of things. So here's the example of the hashing stuff. So you call new for whatever kind of hash that you need, and it gives you a new writer. So you can write byte slices to it, and then you just call sum on it. And as you can see here, here's our data that came into it, and then here's a digest of it. I would show you, I'll run it again to show more random data, but that doesn't actually do anything. So HMAX, when we're doing secret key stuff, or symmetric cryptography, this is what we use for integrity and authentication. So there's other ways to do this, but this is well vetted. It's a well-known way to do it. And the package for doing this in Go is really easy to use. So you can use this, and that'll get you a lot of or give you a strong foundation to build on. It is based on a hash function, so we use it in conjunction with maybe SHA-256. And you need to randomly generate a key for this, or get a key some other way. That package is crypto HMAC. You can see here that the rule of thumb for generating a HMAC key is to just use the size of the digest we're using. So SHA-256 is 32 bytes. We'll generate a 32-byte key for it. And then HMAC, up here, you just tell it, hey, we're using SHA-256. Here's my key. Write some data to this writer, and then get the sum back. And there's actually functions for comparing the HMAX to make sure that it's done securely. There are actual attacks that you can do if you don't do it right. And the Go package authors, Adam Langley, has kindly provided a secure way to do this, so you don't have to worry about implementing it yourself. So let's see. Maybe? Yep, so we just generate some random data, and we can generate tags from that. The output of the HMAC is called a tag. Make sure that they're not the same, and I think that the sandbox actually broke this, so cool. But there's some example code that'll use it. When you guys get a chance to see the slides later, it'll be you guys can look at that. So secret key cryptography, how to use AES and all that. It's hard. It's really tricky. There's a lot of subtleties to it, and there's too much to cover in this talk, so I'm not going to. Use this package called sodium chloride, or NaCl, or whatever, however you pronounce it. It's fast. It's done by a respected cryptographer who also has a reputation for writing good code. If you need to use AES, use Keyzar or something like that, or find somebody who has experience with this. It's really easy to mess up. This is my least favorite package, Crypto X509. It's certificate handling. As of Go 1.3, there's also certificate signature requests, which is nice to have. You can actually do the full generate a key, generate your signature or your certificate request, and then generate a certificate all within Go now. And before, to do that middle step, you had to use OpenSSL or something similar. It's all in Go now. And it also has functions for serializing and parsing your private keys and public keys to the known standards. So you're not trying to how do I compact this? Maybe throw in some JSON. Nope, this has got everything you need. You laugh, but so password hashing, all right? You just throw it in MD5, right? Your password MD5 and store that? No. So there are a couple of things here depending on what you're trying to do. If what you need is a secret key, like you want to use a password to encrypt a file, then we're going to use scrypt. It's really good for doing that. It does require you to generate a random salt, though, 16 bytes or 32 bytes maybe. And you need that salt, which is not a secret, to get the same key back from that password. So one of the things that's really, or one of the ways that you can do that is just when you have encrypted data, you just prepend your salt to that, and that's part of your new format. It's really easy to use, too, and we'll see that in a sec. And then bcrypt, if you're storing a password. Bcrypt's format includes the salt and all the other information that you need to reconstitute that. So it's a good choice for when you want to store a password. You don't have to have a separate column for salt and hash. you can just store this bcrypt result. So here is password hashing. This actually won't run. There's two examples that are based on scrypt and one on bcrypt that won't run on this app engine thing, so I can't prove to you how cool it is. But you can see here it's pretty simple. I have a cleverly chosen password, and we just call generate from password with a cost function. And if you read the docs, it'll tell you what good cost functions to use are. So just you read up your docs before you go throwing this in your code. And then it also has a compare hash and password. So you just give it your password and the previously generated bcrypt hash, and it will tell you whether or not that's right. And if you want to generate a secret key from a password, again, you have your cleverly chosen password, a random salt. I use 16 bytes here. And then we can call scrypt. And there are some default parameters, and there's more choices that you have for this. And the defaults are on the docs. You can also read the RFC or whatever that if you are into that kind of thing. And they will kind of affect how long it takes to get a key from that password. So in other words, if you use stronger parameters, somebody trying to brute force it is going to have a lot harder time doing it. So if you see here, it just gives you a byte slice that you can then use as your key. So I did a quick benchmark here just to show you guys some of the common parameters that are chosen and how it affects password speed. If I could run it, it would be a little bit more interesting, but I don't think it's going to be useful with sandboxing. I didn't think about that. Sodium chloride, I think, is the official pronunciation for this. There is a Go package for it. It uses something, or a cipher called salsa20, and it uses a MAC function that's not HMAC. But they're both well-known, well-proven, and it's very, very fast. In fact, if you don't have hardware support for AES in your machine, this is actually going to be a lot faster. And it's really solid code. And they use a little bit different terminology when you look through the docs. Just know that when you see seal, that means encrypt with authentication, and open means decrypt and make sure or check the authentication on it. Here's an example. Let's see if this one will run. Nope. We're just going to skip it. Does that go okay? Okay, so what cipher should you use? The answer, whatever the RFC says. If you don't know which one to pick, then you should go with whatever it is you're trying to implement says to use. If you're building your own system, then you're probably going to go with sodium chloride, like I said before. Elliptic curves are faster if you need to pick a public key algorithm, but we haven't studied them and we don't have as much experience in understanding the security properties of elliptic curves as we do RSA. So you have to kind of balance those needs there. I have some cipher choices here for TLS. You should prefer ephemeral ECDH, RSA, using AES-128, GCM, and SHA-256. Sounds like nonsense, right? You probably just want to read this off the slide later on. But we picked these, especially like at Cloudflare, where we put a lot of thought into which ciphers are going to be the best for us to serve to people on a large scale. And these we feel are the best performance and security balance for that. And eventually there will be an improvement to Salsa 20 called Cha-Cha 20. And that'll be great for mobile clients because it's faster than AES. And those clients do not have AES support usually on their processors. And when you're picking, like for TLS choices or for your SSL stuff, you really need to have forward secrecy. So you'll see something like ECDHE. There's no excuse anymore not to have that. Just pick one of the ones with ECDHE. And what's forward secrecy? Basically, if somebody compromises your private key, then the previous messages that they may have captured cannot be decrypted. That those messages are secure against that. The fastest one and the most commonly used now is probably elliptic curves for various reasons, mostly speed and performance. But you should pick something like that if you're using TLS. Certificate chains are also the bane of my existence from working on CFSSL, where every CA has their own special and unique way of screwing this up. Yeah. So basically what you have is I'm on example.net, and I want to get an SSL certificate. Okay? So then I have to go to, say, GlobalSign, who's going to issue me a certificate from a private key. But they don't want to put their master key out in the wild, like on a computer that's actually live, because if they lose that, that is a huge cost for them to reissue it and to prove that it belongs to them. There's a lot that goes into that. So they take their master key and they keep it offline. It never goes out on a network computer, or it stays in a hardware security module. And then they have what's called an intermediate certificate, or multiple intermediate certificates. And they sign this intermediate certificate with this offline key, and then they sign your certificate with this intermediate. So if you want to prove that a certificate belongs or was issued by GlobalSign, you walk the chain backwards. I look at your certificate. It says this was signed by GlobalSign's intermediate. Okay, check the signature against GlobalSign's intermediate's public key. And then, oh, this intermediate was signed by GlobalSign's root key. And then they've published the public key. They don't need to keep that secret. So I can look at their public key for the root and the signature on this intermediate and say, okay, it matches or it doesn't. And if everything matches up and lines up, then we know it's a trusted certificate. Well, trusted and reputable for varying definitions of both of those words. There's root pools in X509, which are basically how you choose to, or how you put in a bunch of certificates that you say, we trust these ones. And you'll have an intermediate pool that says, these certificates can be used in the middle of the chain, but they can't anchor a chain. And then you also have a root pool which says, these should be anchors, but probably shouldn't be anywhere else. And the default is your operating system stores. And you'll find some really creative ways that the CAs do this. You'll find older, weaker keys that have been cross-signed and all kinds of fun stuff. So yeah, that's. Yeah. This is one thing that is a pet peeve of mine. Insecure skip verify. Have any of you guys ever used this? Like turn this on? Don't do it. So in the Go session, I had the Samuel Jackson, turn on insecure skip verify one more time. Just don't. What happens is it bypasses all your checks on authentication. So great, you have, if you remember from the beginning, we have integrity and we have confidentiality, but what we don't have is authenticity. So you don't know that you're actually talking to the server you think you're talking to. So you are opened up to things like man-in-the-middle attacks, where I can basically sit in between you and Gmail and proxy things out and read your email, or maybe get a password reset email. You get into some other, like your bank account. So don't do it, because it's really easy to leave it on in production. PEM encoding. This is just kind of like an administrative sort of thing, is that in order to kind of get around some maybe encoding issues with passing binary data around, the standard format is to base 64 the binary data, and then we put some headers on it, like that tells us whether it's a certificate or maybe a private key. And so the Go package encoding PEM does all that, handles all that. You give it a byte slice and you tell it what kind of type it should be, and it'll format everything nicely for you. So generating RSA keys is also pretty easy. You give it your RAND reader, and you tell it how big of a key you want, and it will spit out a key for you, hopefully. So this is what I was talking about with the random number, or the RNG on here. We're going to get the same key each time. So what I do is I generate a key. Or it's a computationally intensive. And this is one of the things about RSA, is it takes a while to do things, except for verifying signatures is really fast. So that's one reason why people sometimes choose elliptic curves over it, is it's slow. But you'll just generate a key, maybe marshal it out into something that you can send off as a, to generate a CSR or something like that. Encrypting with RSA doesn't work like most people think it does, because you normally think that I can have this message, like maybe an email. It's big long message, and then I just pass it to RSA and it encrypts it. RSA actually is limited, if you're using it right, as to how much it can encrypt. It's on the order of 300 bytes. So this is what I was talking about earlier. We agree on a shared key and encrypt that with RSA, and then we switch to that when we want to start sending messages back and forth. So this is a little bit involved, a little bit more involved. We basically generate a random session key and encrypt with RSA, and then now we can encrypt messages with that session key. Signing is pretty similar. You'll see that in the Go package, there's two ways to sign or verify with RSA. There is something called PSS, the Probabilistic Signature Scheme, or PKCS version 1, 1.5. You should use the Probabilistic Signature Scheme, PSS. Use the PKCS 1 version 1.5 only if the RFC or the spec you're implementing to says, hey, use this. There's some math that goes into it that basically the probabilistic scheme is more secure. Generating ECDSA keys. This is what a lot of people use, which you'll see for elliptic curves in TLS, is using ECDSA with the NIST curves. Go provides 3 and maybe 4 standard curves that should get you through pretty much everything that you're going to need to do, unless you're doing Bitcoin stuff. And those curves are called like P256, and then there's one called P521, which is not like a typo, which I thought it was the first time I ran into it, like, oh, you mistyped that. No, it's actually 521 bits. And so they kind of correspond to how strong the symmetric ciphers you're using are. And again, don't worry too much about that, just use what the spec says to use. And then you generate them kind of the same way as you do with RSA. And I think we can actually run this one. It won't take too long. Yes, they're really fast. A lot faster than RSA. So, and if we had seen the RSA key, it would be down to here. So they take up a lot more space. They're bigger keys. So if space is a concern or you really need the speed, then you're going to go with elliptic curves. But again, we don't understand the security properties of them quite like we do with RSA. So you have to balance that out. Encrypting with these curves is complicated. Because we basically have to negotiate a shared key and then switch to symmetric crypto. I'm not going to cover that here because it's a little bit more complicated. So again, the sodium chloride library also has elliptic curves, but they work differently. And the easiest way to use it is just to use the functions in the package for sealing messages and opening messages, and it'll handle all the lower level details for you. You don't even have to worry about how you get the secret key or what the secret key is. So you just generate key. It'll give you a public, private key and throw an error if something goes wrong. And then you can seal and then open the messages. The one thing with this package is you need to make sure you have a nonce, which is a number used once. It doesn't matter how you get that number as long as it's only ever used once. So you could start with 0 and then just keep going up by 1, 1, 1, as long as you make sure that both of you are agreeing on that number and that you're never using it again. So there's some other interesting packages as well. There's OpenPGP. If you guys have seen Keybase, I actually wrote a Keybase half client that handles a lot of the interaction with the site using this OpenPGP package. So you can interact with those keys that way. There's OTR, which is a messaging, like instant messaging encryption protocol. And then there's SSH. Which you can do all the fun that you can with SSH. Here's some real world projects too I included if you guys want to look at them later. Adam Langley wrote Pond, there's Keyzar, an OpenPGP key server, and then the CFSSL that we released. And I think that's all I have. Any questions?
So if I'm using like the standard net HTTP package and as a client and I do an HTTPS request to somewhere, do you know how the cert signing works for that? And what happens if the cert's goes valid or whatever?
So as long as you are validating, which by default the package will, it'll check to see if the certificate's invalid in a couple different ways, but it won't do revocation checks, I don't think. So you might have to check to see if it's revoked yourself. But there isn't really any signing that goes into that, and it's all negotiated in the protocol, which ciphers you're going to use.
So are the root authorities built in binary or using existing stuff?
So for example, with our CFSSL tool that we wrote, you can specify a bundle of certificates, and that'll be your root bundle, for example, and it'll load it up on start and say, okay, here's all of our roots that we're going to trust. And then we have intermediates that we load up on startup too from a file that's similar. And then you can add to that as your program's running. Maybe like in our case, there are times we run into intermediates that we haven't seen before. And as long as adding that intermediate to the chain it still creates a valid chain, we'll add that intermediate to our pool. So it's not built into the binary necessarily. You can, but what most people are going to do is load them from a file. Does that answer the question?
Is that what the kind of standard library does by default?
By default, it'll just use whatever your operating system uses. So if you're using Windows or Linux or Mac, then you have the keychains or certificate stores built or that are distributed with it. Does that answer? Is that
I think so.
okay? Cool. Anybody else? Yep.
Is it better to use the SHA 512 versus 256? Is there any real security difference there?
Can you repeat the question?
So the question is it better to use SHA-256 versus SHA-512? And the answer is you're going to use whatever makes sense with your system that you're building. For example, do you need 32 bytes of output or 64? A lot of what we do is take some data and then kind of mix it up, shuffle up to get some more randomized data from that. And so maybe we need 64 bytes to get a 32 byte encryption key and a 32 byte HMAC key. In that case, you'd use SHA-512. There isn't really a difference in terms of security one way or the other. It's really, I mean, you're going to have less collisions with SHA-512, but it's not appreciable. Anyone else?
What do you do when crypto RAM reader fails?
Tuck your head between your tails and run.
So it does fail on Linux.
if your operating system
Can you repeat the
fails.
question?
Oh yeah, so what do you do if RAND reader fails? And basically that's a failure of your operating system. So you should proceed very carefully. You probably just want to not do anything until that comes back up.
So basically what I did is I just retried.
Yep.
I mean, like, is that what I'm supposed to do?
Yeah, you just you don't want to use bad or like have non-random data. So if it fails, maybe delay for a second and then try again, or some delay time. Anybody else? Cool. Thank you.